but Einstein says objects move along natural paths in curved space-time, and the sensation of gravity is really the sensation of resisting that natural motion. This flips the roles of cause and effect. Instead of gravity causing the curvature is gravity. It's not a force acting on an object, it's the shape of the environment guiding motion. When you try to explain motion using shapes instead of forces, the idea requires a shift in thinking that takes time to settle. Even people who dedicate decades to studying the theory admit that certain parts still feel conceptually strange. The math is clear, the predictions are verified, the theory works flawlessly in experiments. Yet many aspects remain difficult to internalize. It's like learning a new language late in life. You can become fluent, but sometimes your native language still feels more natural. For Einstein's theory, our native language is Newton's physics, the simple rules we grew up with. Those rules worked well enough for everyday life, so replacing them with something more complicated and less intuitive is naturally uncomfortable. Einstein's idea also feels unfamiliar because it implies that our perception of reality is limited. We like to believe our senses give us a complete picture of the world, but if space can bend and time can shift, and we can't detect those shifts without instruments, then our senses are only picking up part of the story. This realization can create a subtle sense of distance between everyday reality and deeper physical reality. That distance has a way of making the theory feel like something we observe from the outside rather than something we live within. There's also the fact that Einstein's work opened doors to questions that became even stranger. Black holes, gravitational waves, the expansion of the universe, singularities, the possibility that time could behave differently in extreme environments. Each of these ideas pushes the limits of what feels natural. So the unfamiliarity doesn't just come from the core theory, it also comes from everything the theory allows and predicts. When you follow the logic of curved space-time, you end up in places where intuition has almost nothing to guide it. And then there's the emotional aspect. When a theory challenges your sense of how the world works at the most basic level, it creates a disconnect. You can accept it intellectually while still feeling unsure about it internally. The theory becomes something you believe rather than something you grasp. That feeling isn't a flaw, it's simply part of the learning process. Space-time is enormous, dynamic, and mathematically complicated. Understanding it deeply requires both patience and a willingness to let go of familiar assumptions. Not everyone feels ready for that shift immediately, and that's okay. If you think back to the first time you heard about relativity, you might remember a moment where the explanation seemed straightforward. Then as you continued listening, it gradually became more complicated. That shift often happens because the first layer is simple. Objects move, time flows, the speed of light stays constant. But the deeper layers require a reorganization of how you picture the world. Instead of imagining fixed space and steady time, you have to imagine something flexible with rules that change depending on motion and gravity. The human mind likes categories. Einstein asks us to blend categories together. And despite all of this, something quietly remarkable happens once you become comfortable with not fully getting the idea. You start to appreciate the beauty of the structure, even if the structure doesn't entirely fit into your intuition. You realize that it's okay for an idea to be partly out of reach. Many of the most important discoveries in science started as things people didn't fully understand right away. The unfamiliarity isn't a barrier. It's a sign that you're dealing with something genuinely deep. There's a moment in the history of science where everything shifted, a point where the seemingly steady world people thought they understood gave way to something deeper, something far more flexible than anyone had suspected. For a long time, people believed the universe was built on fixed foundations. Space was the endless container holding stars and planets. Time was the universal rhythm that never changed its pace. The rules seemed simple. Objects moved, clocks ticked, everything unfolded within a stable stage. Then, little by little, evidence began to appear that the stage itself wasn't as rigid as it looked. What felt like an ordinary backdrop was behaving in ways no one had predicted. And that shift is what eventually led to the realization that space could bend and time could stretch. One way to see how surprising these ideas were is to imagine being alive before they existed. If you looked at the sky at that point in history, you saw a predictable pattern. The planets moved in smooth paths. The sun rose and set. Stars returned to the same positions year after year. There were mysteries, of course, but the overall picture looked steady enough that people assumed space and time must be steady as well. Even when scientists began developing detailed mathematical laws to describe motion, those laws assumed that distances and duration stayed the same, no matter where you were or how fast you moved. It seemed like common sense. Then more precise experiments began to disrupt that sense of stability. One of the first hints came from studying light itself. Light didn't behave the way anyone expected. When scientists tried to measure its speed, they kept finding the same number over and over, regardless of whether Earth was moving toward the light source, away from it, or sideways relative to it. This was strange because for every other kind of motion, speeds add or subtract depending on how you're moving. If you're running and throw a ball forward, the ball's speed is your speed plus the speed of the throw. But with light, no matter how fast you moved, the speed stayed the same. At first, some thought this meant measurements were flawed. Others thought perhaps the universe contained a hidden medium that carried light, something that would keep its speed fixed by design. But repeated experiments showed the same result. No medium was found. Light simply refused to change its speed. This puzzle left the scientific community in an uncomfortable place. The equations describing electricity and magnetism, which predicted the speed of light, had been tested extensively and worked extremely well. But those same equations implied a world where the speed of light was a constant for everyone. If those equations were right, then something else had to give. Either the nature of motion wasn't what people thought it was, or time and space weren't fixed the way people assumed. Most people at that time preferred to believe motion worked the same for everything. After all, that matched everyday experience. But the experiments didn't agree. Into this confusion stepped Einstein, who wasn't trying to be dramatic or revolutionary. He simply wanted the laws of physics to work the same for everyone, regardless of how they were moving. That seemed like a reasonable request. He didn't want different observers to have different laws. He wanted consistency. But in trying to preserve that consistency, he realized something surprising. For the laws to stay the same, space and time themselves would have to adjust. They wouldn't be separate. They would form a single interconnected structure that responded to motion. If one person moved quickly and another stayed still, they wouldn't measure time passing at the same rate. They wouldn't agree on distances in the same way. These differences weren't mistakes. They were built into the universe. This was the beginning of the idea that space could bend and time could stretch. But the idea didn't emerge all at once. It grew from many small steps. Einstein's early papers focused mainly on what happens when objects move at high speeds. He found that time slows down as speed increases. Lengths contract in the direction of motion. These effects weren't noticeable at everyday speeds, which is why people never saw them happening around them. But at speeds close to the speed of light, the changes became significant, and if speed could change the flow of time and the shape of space, then space and time weren't fixed at all. They were flexible. That alone was surprising enough. But the real moment when space began to bend in a literal sense came later, when Einstein thought about gravity again. He knew Newton's description of gravity worked well for most situations. Newton had said gravity was a force pulling objects toward each other, but Einstein wondered whether that picture was complete. If space and time changed with motion, maybe gravity wasn't a force at all. Maybe it was another expression of spacetime's flexibility. That line of thinking eventually led to a startling idea. Instead of seeing gravity as a pull, Einstein began to see it as the shape of spacetime itself. The insight came from a simple question. Why do objects fall? Newton would say they fall because gravity pulls them down. But Einstein considered another possibility. What if the object is actually following a straight path, and the path itself bends because spacetime is curved? In other words, the object isn't being pulled, it's just travelling through a curved landscape. The curve guides its motion. This was a completely different way of looking at gravity. It made gravity less like a tug, and more like a path laid out by the geometry of spacetime. To understand how radical this was, imagine you're rolling a ball across a floor. If the floor is flat, the ball travels straight. If the floor dips or slopes, the ball follows the curve. You don't need to push the ball downward. The shape of the surface determines the motion. Einstein realized that mass does something similar to spacetime. It changes the shape around it, and everything inside that shape moves according to the geometry. That geometry is what we perceive as gravity. But unlike a floor, space-time isn't just a surface with a direction we can point to. It's the four-dimensional structure that includes both space and time. So when space-time curves, it doesn't just curve in a spatial sense. It curves in a way that changes how time flows and how distances behave. This is where the idea of stretching time becomes crucial. If space-time curves, then the flow of time itself can slow down or speed up depending on where you are and how strong the curvature is. Time becomes part of the geometry, not something separate. Think about standing on Earth's surface. You feel the weight of gravity. But Einstein would say what you're actually feeling is the resistance your body provides to avoid falling deeper into the curved path defined by space-time around Earth. Meanwhile, someone floating freely in orbit isn't feeling weight, because they're moving along a natural path determined by that same curvature. They're not escaping gravity, they're following it. They're moving through the curved space-time in a way that feels effortless. The idea that space could bend and time could stretch became clearer with specific predictions. For example, Einstein said that the stronger the gravitational field, the slower time runs. This wasn't metaphorical. It was meant literally. Clocks placed at different heights should tick at different speeds. Decades later, experiments confirmed this. Two clocks, one slightly higher than the other, ticked at rates that differed exactly the way Einstein predicted. This meant the stretching of time wasn't a mathematical curiosity, it was a physical fact. Another prediction was that massive objects would bend light. Since light travels through space-time, and space-time curves around massive objects, the path of light should bend as well. When astronomers observed starlight bending around the sun during an eclipse, the measurements matched Einstein's predictions. This wasn't the sort of bending that could be explained by refraction or atmospheric distortion. It was space-time shaping the path of light itself. The realization that the universe behaves this way changed how people viewed almost everything. Instead of seeing the universe as a collection of objects acting on one another through forces, Einstein revealed a universe where geometry plays a central role. That shift wasn't just a scientific adjustment, it changed the entire mental map people use to understand reality. When you discover that the very foundation of the universe bends and stretches, you have to reconsider what it means for something to move or for time to pass. But even though these ideas are mathematically precise and experimentally verified, they never fully settle into ordinary intuition. It's difficult to imagine time running slower, simply because you're standing closer to a massive object. It's difficult to visualize the curvature of space-time without picturing it as bending into some external space, even though that's not what's happening. And it's difficult to think of gravity not as a pull, but as a path laid out by geometry. Another challenge is that space-time doesn't always bend in gentle, gradual ways. Near extremely massive objects, the bending becomes intense. Black holes are the most dramatic example. At a black hole's edge, the curvature is so steep that not even light can escape the path it's drawn into. Time slows down so dramatically near this region that an outside observer would see the clock of a falling object freeze, even though that object would experience time normally. These predictions are not science fiction. They're direct consequences of space-time's flexibility, and observations increasingly support them. What makes it even more interesting is that space-time doesn't only bend around stars or planets. It bends around anything with energy, movement, pressure, radiation, even empty space all contribute to the shape. The idea that empty space can have energy and influence curvature wasn't immediately obvious. But observations of the universe's expansion show that something in the empty regions appears to be pushing space outward. Whatever this phenomenon is, it's another sign that space-time is much more than a passive container. Thinking about all of this reveals why space bending and time stretching feel so different from the world we encounter daily. In everyday life, distances and durations feel stable, but Einstein's picture shows they're only stable under ordinary conditions, and even then only approximately. The real rules are more flexible. The flexibility remains hidden because our motion is slow, our gravitational environment is moderate, and we don't have instruments in our bodies capable of detecting tiny shifts in space-time. That hiddenness makes the whole structure feel mysterious, yet the bending and stretching aren't strange from the universe's point of view. They're simply how things work. The universe doesn't privilege our intuition. It operates on principles that remain consistent whether or not they feel natural to us. And it's that consistency that allows us to study these effects, measure them, and build an increasingly detailed picture of how space-time behaves, even if the picture doesn't quite match the way our minds naturally try to visualize it. There's a certain comfort in imagining that once we understand a big idea, the smaller details will naturally fall into place, as though the universe is just waiting for us to connect the dots. But when it comes to space-time, the opposite seems to happen. The more pieces we collect, the more we notice that many of them don't quite lock together the way we hoped. Some line up almost perfectly, some sit close but leave small gaps, others fit smoothly on one side but clash violently on another. And the more we examine these mismatched pieces, the clearer it becomes that understanding space-time isn't just a matter of adding new information. It's a matter of figuring out why the pieces aren't cooperating, and whether we're even looking at them the right way. One of the most obvious mismatches shows up in the relationship between the universe on a large scale and the universe on a small scale. Einstein's theory does an extraordinary job explaining how things behave when they're massive and spread out, like planets, stars, and galaxies. It predicts the bending of starlight, the shifting of time in gravitational fields, the movement of galaxies, and even the ripples produced by black hole collisions. When astronomers measure these things, the results consistently follow the predictions. That's an impressive achievement, and it's part of why his work became one of the pillars of modern physics. But the smaller scale is ruled by something entirely different. Quantum mechanics governs atoms, particles, fields, and all the strange behaviors that happen in the microscopic world. Instead of smooth curves and continuous geometry, quantum mechanics deals with probabilities, fluctuations, jumps, and uncertainties. It doesn't describe motion the same way relativity does, it doesn't treat time the same way, and it doesn't treat space the same way. While relativity says space-time is a smooth, continuous structure, quantum mechanics suggests that nothing is truly continuous. Every field fluctuates, every position has uncertainty, every event has probabilities attached to it. If space-time were just another physical field, quantum mechanics would suggest it should fluctuate too. It should jitter, ripple, or break into tiny units. But at the scales we can measure, space-time appears calm and smooth, not jittery or grainy. This creates a tension between what the two major theories predict. Relativity demands comforting smoothness. Quantum mechanics demands restless motion. These demands can't both be right in all situations. Something must give. The mismatch becomes especially noticeable when you look at places in the universe where both theories should apply at once. Black holes are the clearest example. At the center of a black hole, relativity says the curvature of space-time becomes infinite. Everything collapses into a region with no volume at all. This is called a singularity. The equations break down there, not because the math is incomplete, but because the predictions become nonsensical. Dividing by zero, infinite density, infinite curvature, infinite something or other that no physical process can handle. Relativity wasn't designed to deal with infinities like that. It signals that it has taken itself as far as it can go. Quantum mechanics, meanwhile, doesn't allow infinities either. It insists that quantities remain finite, and that the universe has limits on what can be squeezed or stretched. So when you ask what happens at the very center of a black hole, the two theories argue. Relativity predicts a singularity. Quantum mechanics predicts something else entirely. But neither theory can take over completely because both are essential near a black hole's core. The mismatch leaves a void in our understanding, a place where the pieces don't fit and the picture becomes blurry. A similar problem arises when studying the very beginning of the universe. According to the best models, the universe started in a state of extremely high density and temperature. Relativity can roll the clock backward and describe the expansion of the universe until the numbers get too extreme. Then the equations fail, pointing again toward a singularity. But that singularity isn't a physical object. It's a sign that the theory isn't equipped for the job. Quantum mechanics should be able to help because the early universe was tiny, and tiny things fall under its domain. But quantum mechanics also fails when gravity becomes overwhelmingly strong. The two theories don't cooperate. They talk past each other like two experts from different fields, who both know they're right but can't agree on a common language. This incompatibility creates an uncomfortable feeling. We have two incredibly successful descriptions of nature, both verified by countless experiments, and yet they can't be merged smoothly. It's like owning two excellent maps that overlap but don't connect at the edges. Each one is reliable on its own, but when you try to place them together, the roads don't line up. The rivers bend in different places, the borders don't match, and that's unsettling because a complete understanding of space-time requires a map that covers everything without contradictions. The universe doesn't divide itself neatly into the large and the small. The same reality must obey a single consistent set of rules, even if we haven't found them yet. Another piece that doesn't quite fit comes from trying to understand what actually causes space-time to bend. Relativity says mass and energy shape the geometry, but that explanation doesn't reveal the underlying mechanism. Why does mass cause curvature? Why does energy distort the geometry around it? Why does space-time respond at all? The equations show how curvature behaves. They don't explain why the relationship exists. This leaves a gap. It suggests that space-time's behavior may be more fundamental than relativity describes. Something deeper might be influencing the geometry, something we haven't identified. Then there's the question of whether space-time is truly smooth, or whether it only appears that way at the scales we can observe. Some theories suggest that space-time might be made of tiny discrete units, much smaller than atoms, smaller than any particle we've ever detected. If space-time had a granular structure, it would mean the smooth geometry of relativity is only an approximation, not a complete description. But if it does have such a structure, our tools aren't sensitive enough to detect it. We can't confirm or deny it. That uncertainty creates another mismatch, a place where the pieces remain ambiguous. Emergent space-time is another idea that floats around in the world of theoretical physics. According to this idea, space-time might not be fundamental at all. Instead, it might arise from deeper physical processes the way temperature arises from atoms in motion. A single atom doesn't have a temperature, but a large collection of atoms does. Similarly, the universe might contain some underlying ingredients that produce space-time when combined in large numbers. If that's true, then space-time itself might not exist at the smallest scales. It might show up only when enough of the underlying components interact in a particular way. This idea is intriguing, but it leaves us with puzzles. If space-time emerges from something else, what is the something else? How does it produce geometry? And why does the resulting geometry behave the way it does? Another puzzle piece that doesn't fit cleanly involves something called vacuum energy. Quantum mechanics predicts that empty space is never truly empty. It's filled with fluctuations, tiny bursts of energy appearing and disappearing constantly. When physicists calculate how much energy these fluctuations should create, the number they get is staggeringly large, far too large to match what we observe in the actual universe. The predicted value and the real measured value differ by an amount so enormous that it's often called the biggest mismatch in the history of physics. Relativity says energy affects curvature. If empty space contained as much energy as quantum mechanics predicts, the universe would curl up instantly or expand at an unbelievable rate. But neither of those things happen. The observed universe expands at a perfectly manageable pace. This means the calculated vacuum energy must be wrong, or relativity's relationship between energy and curvature must be incomplete, or both. Another example of two puzzle pieces refusing to click together. Dark energy offers another mismatch. Observations show that the universe is expanding faster over time, not slower. Relativity allows for this behavior if you include a term in the equations that acts like a repulsive energy spread through space. But no one knows what this energy is. We can measure its effects, we can describe the way it works mathematically, but we don't understand the origin or the mechanism. It behaves like a property of space-time itself, something built into the geometry. But it doesn't fit with quantum predictions, and it doesn't match anything we've seen in experiments. It sits uneasily between theories, as though pointing toward a missing piece we haven't recognized. Dark matter creates a different sort of mismatch. Galaxies spin faster than they should if all the mass inside them were visible. Stars at the edges move so quickly that based on visible mass alone, they should fly away into space. But they don't. Something unseen provides extra gravitational pull. The simplest explanation is that there's invisible matter we haven't identified. But no particle we've predicted or discovered fits the behavior perfectly. Relativity explains how the invisible mass shapes the geometry, but the nature of the mass remains unknown. another puzzle piece with no clear home. A more subtle mismatch comes from the role of time. In relativity, time is woven into space-time and treated as a dimension. But in quantum mechanics, time isn't treated the same way. It doesn't become part of a unified geometry. Instead, it remains an external parameter, a backdrop against which events unfold. This creates tension. How can time be part of space-time in one theory, but a separate parameter in another? The two pictures don't align, and until they do, any unified picture remains incomplete. Even the way forces behave is divided. Relativity describes gravity not as a force but as a geometric effect. Quantum mechanics, meanwhile, describes all other forces using particles and fields. Gravity doesn't fit into this framework cleanly. Attempts to treat gravity as a quantum force run into contradictions. Trying to describe space-time as a field on top of a fixed background doesn't work because space-time is the background. Trying to quantize the geometry leads to mathematical results that blow up or collapse. Each approach reveals useful insights, but ultimately runs into walls that signal something missing. These walls aren't failures. They're clues. They show us that the pieces we're working with belong to a larger puzzle, whose outline isn't fully known. Another mismatch appears when you look at the concept of locality. Relativity insists that nothing can influence anything else faster than the speed of light. Quantum mechanics, on the other hand, allows entangled particles to appear correlated instantly across distances. These correlations don't transmit useful information faster than light, so relativity isn't technically violated, but the deeper explanation remains unclear. Does space-time allow this instant matching of states because it has some structure we don't understand? Or do the correlations hint at something that lies outside space-time altogether? All of these mismatches create an unusual kind of tension in physics. We have a clear picture on large scales and a clear picture on small scales, but the two pictures don't merge into one. They stand next to each other, accurate within their own domains, yet unable to overlap smoothly. That tension makes space-time feel unfinished, as though we're working with a set of tools designed for different jobs that haven't yet been combined into a complete toolkit. And rather than discouraging scientists, these mismatch pieces have encouraged deeper exploration. Each gap, contradiction, or unexplained result points towards something new waiting to be discovered. It's hard not to feel a certain curiosity when thinking about how the universe behaves at its smallest scales, especially after spending so much time with the more gradual curves and smooth structures of space-time. When everything is large enough to see, or even large enough to imagine without effort, the world feels steady. It makes sense that planets orbit, that objects fall, that light follows predictable paths, and that time moves forward in a controlled rhythm. But when you shrink the picture down to the tiniest regions, past atoms and into the realm where particles flicker in and out of existence, all that steadiness falls away. The rules you thought you knew stop applying. Patterns break. Certainties dissolve. And instead of behaving like orderly pieces in a grand cosmic machine, the components of the universe act like they're following instructions written in a language that doesn't quite match anything else. This shift from the smooth structure of space-time to the restless behavior of quantum rules is one of the main reasons the pieces of the cosmic puzzle never quite fit together. The two sides of physics describe the same universe, yet they speak entirely different dialects. On one side, space-time bends and stretches predictably. On the other, particles jump, fluctuate, and ignore many of the expectations we bring with us from everyday experience. It's almost as if the universe uses a different playbook when it's looking at the microscopic scale, and it doesn't bother explaining what changed. Trying to make those two perspectives align is like trying to solve a puzzle whose pieces reshape themselves whenever you glance away. One of the first surprises that emerges when you look closely at quantum behavior is that particles don't seem to have definite positions until you measure them. In everyday life, objects stay where you put them. A cup doesn't smear itself across the counter just because you're not looking at it. But at the quantum level, particles don't sit still in fixed, predictable places. They spread out into probability clouds that describe where they're likely to be. And until something interacts with them, there's no single location you can assign. The universe doesn't treat position as a fixed attribute. It treats it as a shifting range of possibilities. This leads to one of the earliest lessons you encounter in quantum mechanics, the idea of uncertainty. Not uncertainty in the sense of, we're not sure because we haven't looked hard enough, but uncertainty built into the structure of the universe itself. The more precisely you try to measure a particle's position, the less precisely you can know its momentum. The reverse is equally true. It's not a matter of using better instruments. The limitation is woven into the fabric of the quantum world. This behavior stands in sharp contrast to relativity, which describes things in terms of smooth geometries and continuous paths. There's no uncertainty in the bending of space-time. Everything follows a clear trajectory, determined by the curvature. But in the quantum world, trajectories dissolve, paths blur. The concept of a definite track becomes something the mathematics can't provide. This creates an immediate conflict with the expectation set by space-time. Another strange rule arises from the way particles behave as both waves and particles at the same time. If you send particles like electrons or photons through a pair of slits, they create an interference pattern, the kind you would normally associate with waves spreading and overlapping. But if you try to observe which slit each particle passes through, the interference disappears and the particles behave individually instead. The simple act of observing changes the result. This isn't because the observer is doing anything dramatic. It's because the rules of the quantum world involve probabilities that only collapse into a definite outcome when measurements occur. Before that moment, the possibilities remain spread out, coexisting in a way that has no counterpart in the larger world. This dual nature is hard to reconcile with the smooth geometry of space-time. Space-time doesn't decide which path an object takes only after someone looks. It doesn't have categories that shift depending on observation. It's built on predictable relationships between mass, energy, and curvature. But quantum mechanics isn't built that way. It's built on probabilities, wave functions, and sudden changes that have no equivalent in relativity. The universe doesn't seem bothered by the inconsistency, but humans have a harder time with it. Trying to imagine something that behaves like a particle and a wave simultaneously stretches intuition past its usual limits. Another frustrating aspect of quantum rules is the way particles can become entangled. When two particles become linked through a quantum interaction, their states remain connected regardless of how far apart they move. If you measure one particle, the other instantly reflects a matching result. There's no signal traveling between them that we can detect. The connection doesn't weaken with distance. It simply remains. This seems to violate one of the most cherished principles of relativity. Nothing can influence anything else faster than the speed of light. Yet quantum entanglement does something that looks suspiciously like faster-than-light influence, even though it doesn't technically transmit information. It creates a kind of correlation that's impossible to explain using only the smooth rules of space-time. This mismatch leads to a deeper question. Does entanglement occur within space-time, or does it operate outside of space-time altogether? If it occurs within space-time, then its instant connections don't make sense. If it occurs outside of space-time, then what does outside even mean? Does the universe contain a deeper structure that underlies space-time and allows these correlations to happen? Or does space-time fail to describe the universe at the quantum level, meaning its rules apply only on larger scales? These questions don't have clear answers yet. They sit between theories, pointing toward gaps we haven't found a way to bridge. The quantum world also behaves in ways that seem unnecessarily restless. Even in a perfect vacuum, where no particles should exist, quantum fields fluctuate. These fluctuations cause tiny bursts of energy to appear and disappear constantly. It's as if the empty regions of the universe never sit still, even for a moment. Relativity describes empty space as a smooth background that can bend and stretch, but it doesn't include the restless jitteriness that quantum mechanics predicts. And when physicists try to calculate how much energy those fluctuations should add to the vacuum, the result is far too large. If the quantum prediction were right in full detail, space-time would curve so dramatically that the universe would collapse or expand uncontrollably. But that doesn't happen. So something must be off, either in the calculations or in the assumptions behind them. Another place where the quantum rules refuse to behave nicely is in their treatment of time. Relativity treats time as part of the geometry of space-time, a dimension shaped by mass and motion. Time flows differently depending on where you are and how fast you're moving. It's dynamic and flexible, but in quantum mechanics, time plays a very different role. It acts as a fixed parameter, something that ticks forward at a uniform rate for all systems, Regardless of the forces or conditions involved, there are no time loops or shifts or curves in the basic equations. Time doesn't stretch or bend, it stays put. This difference creates a major conflict. If time is part of space-time and space-time curves, then time should curve too. But quantum mechanics doesn't allow its version of time to curve. It doesn't even treat time as something that can respond to forces or geometry. That mismatch leaves physicists with equations that work extremely well, but don't match each other at a fundamental level. Another challenge appears when trying to combine gravity with quantum rules. Every other force in the universe can be described using particles that carry the force, photons for electromagnetism, gluons for the strong force, and so on. If gravity were like these forces, it would have a particle called the graviton. But trying to describe gravity using a graviton leads to mathematical problems. The calculations blow up into infinities that can't be removed or simplified. This suggests that gravity doesn't fit into the quantum framework the same way the other forces do. It behaves more like geometry than like a field. But if gravity is geometry, how can it be quantized? How can the shape of space-time itself become probabilistic or uncertain? The attempt to answer these questions has led to numerous theories, each with its own set of assumptions, but none have been proven correct. Even the idea of a particle raises questions when you look at it too closely. In quantum field theory, particles aren't tiny, solid objects. They're excitations of underlying fields. An electron isn't a miniature sphere, it's a ripple in the electron field. A photon is a ripple in the electromagnetic field. These ripples follow quantum rules, and they can overlap, vanish, or reappear in ways that don't resemble how objects behave in daily life. But if particles are ripples, what does that make space-time? Is it a field too? If so, what kind of field? And how does that field ripple? These questions circle back to the earlier mismatch between smooth geometry and quantum uncertainty. Ripples in space-time would be gravitational waves, and those have been detected. But the waves behave differently from other field excitations. They're incredibly weak, gentle compared to the restless fluctuations predicted by quantum mechanics. It's unclear whether the two pictures can be reconciled. Another odd rule emerges when considering how quantum mechanics treats measurement. In relativity, measurement is straightforward. You measure distances, times, or velocities, and the values follow the geometry. But in quantum mechanics, measurement changes the system being measured. The wave function, which describes the probabilities, collapses into a definite outcome. Before the collapse, the system behaves as a superposition of possible states. After the collapse, it behaves like a classical object. No one knows why this collapse happens or what exactly triggers it. Some theories suggest it's a physical process. Others suggest it's an informational update. Some propose that collapse never happens and that all outcomes exist in parallel. But none of these explanations fit smoothly into the geometric picture of space-time. If measurement changes the system, does space-time play a role in the collapse? Does collapse affect the curvature of space-time? If so, how? The theories don't agree. Another curious aspect is how quantum mechanics treats motion. In relativity, motion follows clear paths called geodesics. But in quantum mechanics, motion becomes a matter of probabilities. Particles don't travel from point A to point B on a single path. They take all possible paths, and the probabilities interfere to produce the final outcome. This picture is radically different from the smooth curves of space-time. Trying to merge these perspectives creates contradictions. If a particle takes all paths, does it sample all possible curvatures of space-time along the way? Does space-time shape the probabilities, or do the probabilities shape the curvature? These questions sit at the intersection of two incompatible theories. Even the vacuum behaves differently in the quantum picture. In relativity, empty space is neutral. In quantum mechanics, empty space is never empty. It seethes with temporary particles that appear and vanish. If space-time were fully compatible with quantum rules, this seething should affect curvature dramatically. But it doesn't. Something keeps the quantum fluctuations from dominating space-time, even though the theory says they should. The lack of agreement between prediction and observation is one of the biggest mismatches in all of physics. Another rule that refuses to behave comes from the idea that quantum systems don't have definite properties until they're measured. In relativity, objects carry their properties with them regardless of who observes them or how. But in quantum mechanics, the act of observation creates definite properties where none existed before. This introduces an observer-dependent element into the theory that relativity doesn't include. Relativity insists that physics must be the same for all observers. Quantum mechanics suggests that observers play a role in shaping the outcome. These views can't be easily reconciled. Each of these strange rules contributes to the sense that quantum mechanics, while accurate in its predictions, behaves like it belongs to a different universe entirely, and yet it describes the same reality we live in. That mismatch, that refusal of the quantum world to align itself neatly with the rules of space-time, creates a tension that won't go away. It pushes physicists to search for a deeper theory that might unify these behaviors, a theory that explains why the quantum world behaves so differently and why space-time behaves so smoothly. There's something quietly puzzling about gravity when you sit with it long enough. It's one of the first things we learn to recognize long before we know the word for it. You feel it every time you drop something, every time you stand up, every time you watch an object fall. It's familiar in a way that almost nothing else in physics is. You don't have to explain gravity to a small child for them to know that things fall downward. It's built into everyday experience, woven into each moment without needing any attention at all. And because it's so ordinary, it's easy to forget how mysterious it really is, especially when you compare it to the other forces and behaviors that shape the universe. Gravity has a softness to it, a quiet influence that feels gentle next to the sudden jumps and unpredictable patterns of the quantum world. Yet despite its familiarity, gravity is the one area where our understanding reaches a hard limit, faster than almost anywhere else. One of the first things that makes gravity so strange is how incredibly weak it is compared to other forces. It's strong enough to keep you anchored to the floor, strong enough to shape planets and stars, strong enough to control the structure of galaxies, yet the amount of mass needed to produce those effects is enormous. If you compare gravity with something like electromagnetism, the difference becomes almost unbelievable. A small magnet on your refrigerator can easily overpower the gravity of an entire planet when it pulls a piece of metal upward. That means the force holding that little piece of metal to the fridge is stronger than the force Earth exerts on it. Somehow, the force that shapes the entire cosmos is weaker than something sitting quietly on your kitchen appliance. This mismatch in strength leads to an uncomfortable question. If gravity is so weak, why does it dominate the large-scale behavior of the universe? The answer lies partly in the fact that gravity always attracts. Other forces can push or pull, cancel out, or reverse direction. Gravity only accumulates. Every bit of mass adds to the total pull. There's no negative mass to counteract it. This means that even though gravity is weak on small scales, it becomes incredibly significant when large amounts of mass collect. But the deeper question still remains. Why does gravity behave so differently from everything else? Why is it so gentle compared to the other forces? And if it's a completely different kind of interaction, is that why it refuses to merge smoothly with quantum rules? Another thing that makes gravity feel mysterious is the way it acts on everything equally. Electromagnetism applies only to charged particles. The strong and weak forces act only inside atoms. But gravity applies to anything with mass or energy. It doesn't care what the object is made of. It doesn't care whether it's charged or neutral. It doesn't care whether it's sitting still or moving. It acts consistently on every physical thing. This universality is part of what led Einstein to the idea that gravity might not be a force at all, but a feature of space-time. If something affects everything the same way, maybe it's baked into the structure of reality. Maybe it doesn't push or pull. Maybe it simply shapes the paths things naturally follow. Einstein's view of gravity as curved space-time worked brilliantly for explaining many observations, but it also created new questions. If gravity isn't a force, then what is the underlying nature of this curvature? What does it mean for space-time to bend? Why should mass cause curvature in the first place? The equations describe the relationship with great accuracy, but they don't reveal the mechanism. It's a bit like having a perfectly reliable set of instructions for how something behaves, while still not knowing what the object itself is made of. You can predict it, you can measure it, you can confirm its effects, but you can't quite say what it really is. One of the clearest places where the limits of our understanding show themselves is inside black holes. These objects form when matter collapses under its own gravity, to the point where nothing can escape, not even light. Einstein's equations predict exactly how black holes distort space-time near their edges. They describe how objects would fall into them, how light would bend around them, how time would slow near them. All of that matches observations, but the equations break down when you try to describe what happens at the very center. The curvature becomes infinite, and quantities that should stay finite explode into impossible values. This breakdown isn't a sign that the universe falls apart at that point. It's a sign that our understanding does. Gravity pushes our theories into regions where they stop working. It's almost as if the universe quietly tells us, "You've gone as far as these tools can take you. Something else is needed from here onward." And no matter how hard physicists try to refine the equations, the singularity remains a reminder that the story of gravity isn't finished. Another area where gravity tests our limits is in the behavior of the universe as a whole. When astronomers predicted how galaxies should rotate based on the gravity of the visible matter inside them, the results didn't match the observations. The edges of galaxies were rotating much faster than they should have been. Instead of slowing down with distance, their rotation curves stayed flat. Gravity was stronger than the visible matter could explain. The simplest explanation was that there must be more mass than we can see, something invisible but heavy enough to create the additional pull. That idea became known as dark matter, but decades later, no one knows what dark matter is. It hasn't been detected in a laboratory, it doesn't emit light, it doesn't interact with electromagnetism, it shapes galaxies, yet refuses to reveal itself in any direct way. This leaves gravity acting as a messenger for something we don't understand. It shows us the effects but hides the source. A similar problem appears with dark energy. Observations show that the universe is expanding, and not only expanding but accelerating. Something is pushing space-time apart, something with negative pressure, something that causes expansion rather than contraction. Again, gravity is the messenger. It shows that space-time is stretching faster than it should, but it doesn't tell us why. The equations can accommodate this behavior by adding a term, but the origin of that term remains unknown. So gravity creates curves and stretches that point to phenomena we don't understand. It highlights patterns but withholds explanations. These puzzles become even more challenging when we try to connect gravity with quantum mechanics. Quantum mechanics describes the behavior of particles and fields with extraordinary accuracy. Gravity describes the behavior of space-time equally well on large scales. Both theories are pillars of modern physics, yet they don't merge. Attempts to combine them lead to contradictions. In quantum mechanics, forces are carried by particles, but treating gravity as a force carried by particles leads to mathematical explosions that can't be resolved. In relativity, gravity isn't a force carried by anything, it's the shape of space-time, but trying to describe space-time as something quantized doesn't match smoothly with the existing framework of quantum field theory. Each approach works beautifully on its own, but they refuse to behave when brought together. This is where the nature of gravity creates one of the biggest tensions in physics. If gravity is geometry, then the quantum behavior of particles must take place inside that geometry. But if space-time itself becomes uncertain at small scales, then the geometry must also be affected by quantum rules, which means gravity should be quantized too. But each attempt to quantize it leads to inconsistencies that don't arise with the other forces. It's almost as if gravity sits at the edge of both theories, touching each one but belonging fully to neither. One reason this problem is so hard is that gravity doesn't shield itself. Other forces have ways of weakening or cancelling out. Electromagnetism can be neutralized by opposite charges. The strong force is confined to tiny regions inside atoms, but gravity extends everywhere. It cannot be blocked or isolated. You can't create a region where gravity is turned off to study it in isolation. You can't shield an experiment from gravitational influence the way you can shield it from electromagnetic fields. Gravity's reach prevents us from separating it from the rest of reality, which makes it extremely difficult to study under controlled conditions. That lack of isolation is part of why the deeper nature of gravity remains hidden. Another problem is that gravity becomes much stronger relative to other forces only at incredibly high energies or in extremely dense regions. The quantum effects of gravity would show up at energy scales far beyond anything we can achieve with current technology. The universe doesn't give us many opportunities to observe gravity in those extreme environments either. Black holes provide one, but their centers are hidden behind event horizons. The early universe provides another, but we can't directly observe the first tiny fraction of a second after the Big Bang. So the conditions where gravity and quantum mechanics collide are precisely the conditions we cannot access experimentally. That lack of direct evidence leaves theorists working with mathematics, looking for a structure that brings everything together without contradicting known physics. Another subtle difficulty lies in the way gravity defines the stage on which all physical processes happen. Quantum mechanics assumes a fixed background, a stage that doesn't change. But gravity refuses to provide such a stage. It curves the background. It changes the distances, the timing, the geometry. It shapes everything, including the stage itself. Trying to place quantum rules on a stage that constantly changes leads to calculations that spiral into impossible values. This creates a circular problem. Quantum mechanics needs a fixed spacetime to function smoothly. Gravity insists that spacetime is never fixed. Even the simplest question, such as what happens at the exact point where a particle interacts gravitationally with spacetime, becomes tangled. Does the particle create a ripple in spacetime? Does the ripple have a quantum nature? Are these ripples smooth or grainy? Does the geometry itself fluctuate? How do these fluctuations interact with the particle's own fluctuations? Each question branches into new ones, and each branch reveals more gaps in our understanding. These limits aren't signs that physics is failing. They're signs that physics hasn't reached the full picture yet. They show the edges of our current framework, and gravity is one of the main places where those edges become obvious. It doesn't resist being understood. It simply reveals its complexity slowly, piece by piece, as though encouraging us to look more closely. What makes this even more interesting is that gravity doesn't behave differently out of stubbornness. It behaves differently because it's tied to the fundamental shape of the universe. Everything that happens in the cosmos depends on the geometry created by gravity. The structure of galaxies, the behavior of planets, the bending of light, the expansion of the universe, the slowing of time near massive objects, the patterns formed by matter and energy, all of these things follow the quiet influence of gravity. Yet gravity remains the least understood of all the major interactions. There's a peculiar kind of tension that appears when you try to make sense of the universe from two completely different angles. On one side, there's the world of massive things, the realm where galaxies stretch across unimaginable distances and stars burn for billions of years. On the other side, there's the world of the tiny, where particles flicker, jitter, and swap identities in less time than it takes to blink. Each side has its own rules, its own language, its own sense of logic, and in a strange way, each side behaves beautifully on its own. The large-scale universe follows the predictable curves of space-time. The small-scale universe follows the restless dance of quantum mechanics. Neither side seems particularly bothered by the other until you try to bring them together. That's when the arguments start. It feels a bit like listening to two people describe the same story from completely different viewpoints, both convinced they have the correct version. The large-scale description relies on smooth shapes and gradual shifts. The small-scale description relies on probabilities and sudden jumps. If the universe behaved like one or the other, things would be simpler. But reality insists on using both at the same time, and that insistence creates a set of problems that have kept scientists puzzled for decades. A natural place to start is with the fact that space-time, as described by Einstein, is continuous. It curves gently around massive objects. It stretches during cosmic expansion. It creates the paths that planets follow, and the timing differences we measure with precise clocks. Everything about it suggests a smooth structure, something you could, in theory, zoom into endlessly without encountering individual pieces. But the quantum world doesn't believe in smoothness. It insists on uncertainty. It insists on fluctuations. It insists that nothing can be perfectly still or perfectly defined, no matter how small you go. This difference in how each side sees the universe creates an immediate conflict. If space-time is smooth, then the paths particles follow should also be smooth. But quantum mechanics says particles don't follow well-defined paths. They smear out into a range of possibilities. They can be in two places at once in a probabilistic sense. They don't move along tidy curves. They follow patterns that only become clear when you look at them statistically. So if you try to describe a particle moving through curved space-time, you end up trying to force these contradictory views to cooperate. The smooth curvature of relativity doesn't blend easily with the fuzzy probabilities of quantum mechanics. Another conflict shows up when you examine how each theory treats energy and motion. In relativity, energy is tied directly to the curvature of space-time. More energy means more curvature. The relationship is clear and consistent, but in quantum mechanics, energy fluctuates constantly, even in empty space. These fluctuations happen at such high frequencies and short timescales that they would create dramatic curvature